G'day, I'm Joe Wolfe, one of Liz's colleagues here at UNSW. You'll notice that when she discussed the vibration of bars, we couldn't use the simple one-dimensional equations. We couldn't get the frequency just by using the speed of sound and the length of the medium that's vibrating. There is, however, a percussion instrument where you can do that, and it's called the stroke rod, and there it is. I like to think of it as being analogous to a flute. It's just a cylinder of metal, and the flute, if we close all of the holes, is a cylinder of air. And because with the flute you blow over the top hole, you leave that free, air can go in and out, air can go in and out, so you have a displacement antinode at both ends, a node in the middle, and so the lowest mode on the complete flute would be speed of sound divided by twice the length of the instrument, and you do that and you get about 260 Hertz, which is about middle C. And then if you consider the other modes, you can have a mode that's twice that frequency, 3 times, 4 times, 5 times, and so forth, and you can excite those by blowing harder and harder. And so forth. I'm mixing them up there. Let me just see if I can get those in order. Yeah, okay, so there's the first 7 modes on that cylinder of air. Now think about the pitch in the stroke rod. Metals are several thousand times denser than air, so that would make it lower, but they're also about 1,000,000 times stiffer than air, 1,000,000 times less compressible, and the speed of sound goes as the square root of the elastic property over the mass property, here the density, and so the speed of sound in steel, say, is about 20 times faster than in air. So that means that this stroke rod here is a soprano stroke rod. Now, free at both ends, so a displacement antinode at either end, just like the flute. And I'm going to create a node at the middle with my fingers. And the way that we excite longitudinal vibrations here is using a cloth and some weightlifter's rosin. Oh. That's the first mode, not very loud. And if I hold it about here, oh, there we go. That's the second mode up there with a node where I have my fingers. So a bit of an unpredictable instrument to play. Let me go for the first mode again. So there it is. That's a wave with antinode, node, antinode, but a high speed of sound in the metal. If I can tell a story about that, a friend of mine, Colin Piper, played percussion with the Sydney Symphony for a long time, and every now and then a piece would require him to play the stroke rod. And he used to say, well, I'd be up the back of the orchestra with my hand in a gardening glove and a bunch of weightlifters' rosin, and if the instrument doesn't play, I'm going to look really silly.
Let's try a problem about stroke rods. So the question is, a 3-meter steel rod is held at its midpoint and stroked to generate longitudinal waves. What is the fundamental frequency for this rod gripped in this way? The speed of sound in steel is 5,800 meters per second. Okay, so let's start by drawing a diagram. Here we have a 3-meter long rod, and it's gripped halfway along. So we're going to force there to be a node halfway along like that. So we can end up with a standing wave, which looks like this. So we've got quarter of a wavelength in each half of the rod. So our wavelength is going to be double the length of the rod, or 6 meters. So we've got our wavelength, and what we want to know is the frequency. We've got the speed is 5,800. So we can use V equals F lambda to give us F is equal to V over lambda. And so that's 5,800 over 6. And solving this, we end up with 967 hertz. So that's around about 1,000 hertz is the fundamental frequency for that rod held in that way.
Bells are another type of percussion instrument. This singing bowl is actually an example of bells. So typically with bells you hit them and they resonate at certain frequencies. So we get standing waves set up over the surface, and it'll depend on the material that the surface is made from, as well as the shape of the bell, what sound we actually hear. Now, a nice way of showing this resonance phenomenon with the singing bowl is to actually fill it with water, like I've done. And then when you stroke around the outside, setting up a resonance, the water will actually make a pattern on its surface. So that's a nice example of a resonance effect. Drums are another type of percussion instrument. When I hit the drum, I get standing waves set up in the surface. So one possible mode of vibration is with the center going up and down, up and down, up and down. I can also have a mode of vibration where the two edges are going up and down at different times, or another one set up like this. So up here you can see some of the different types of standing wave patterns that I can set up on a typical drum. Now, because there's no nice integer relationship between all of these, we don't hear the harmonics for a drum like we hear in other musical instruments. So below I've linked to a video where you can see what happens when you play different frequencies through a large membrane. You can see the sand sprinkled over the membrane, which is showing you the different patterns that the surface of that membrane makes up.